All right, good afternoon, everybody. It's my pleasure to welcome you to a talk by Dr. Kuang, who gladly accepted to speak to our chapter today. So he is a professor of mathematics at Arizona State University since 1988. He authored more than 180 journal publications, as well as 16 books. He is also the founder and editor of the Mathematical Bioscience and Engineering Journal, and has directed more than 23 PhD dissertations in mathematical and computational biology. And today he's here to talk to us about traveling wave solution and some reaction diffusion model of glioblastoma growth. So the floor is yours. Thanks for speaking again.
Thank you, Maxime, Emmanuel, and also Justin, I guess, for making the connection. It's really a pleasure to actually get connected to Professor Yan and Lin and all the friends. And I only wish that it's not because COVID-19 I could fly over and to enjoy the better weather. We have actually dealt with COVID-19 very well, and so I hope you guys are doing well too. The reason I want to sort of like choose this topic really for the tiny list and also for the sort of like challenges that continue to actually challenge in the whole scientific community. We are really sort of like invested a lot of, I mean, the whole medical community spent the last 3-4 decades trying to cure, of course, cancer, in particular, the glioblastoma, the brain tumor that killing most of patients. And really is a deadly tumor. Maybe I'll get into the next slide very quickly. So thank you for the opportunity. I will try to focus on the modeling aspect because the mathematics can go either very complicated or can go to very sort of routine computational details that may or may not be necessary or interesting. So the reason I like to call traveling wave for many sort of us interesting PDE models, because oftentimes what you observe as a solution really often takes the form of traveling wave if the equation including the motion that governed by what we call random motion. Or random motion is one of the primary sort of mechanism, sort of moving the particles or moving the cells. And then the default sort of like choice for many people working in mathematical biology is to first assume the motion is indeed random or using the what we call fixed law, so moves from the high gradient to low gradient. So that's sort of like making the traveling wave solution became sort of like a natural topic, not just mathematically interesting, but also really is what you're going to observe in reality, and also what you're going to see computationally. And then how that connect to diseases, and then in this case, brain tumor, you're going to see in a quick time. I mean, in the next picture, actually, next slide. So you can see I put the Chinese sort of like slides here because the last time I gave this talk was actually to my Chinese colleague in actually Northeast Normal University. And then just in case they ask a question, I don't know the answer. So here I provide that. And then I'm glad two Chinese colleagues here too. But really, the GBM is just so well known in the community, like us, also in the political sort of like sort of landscape that we see last year. Indeed, Joe Biden, the reason Joe Biden didn't run 4 years, or the reason Joe Biden did run last year for the presidency, because of his son died of GBM, the ball. And then he was grieving, and it was really deeply sort of hurting 4 or 5 years ago. And even this year, before he sort of leave for the White House, he really think that his son should be the one that moving to the White House because his son is just great son. or great sort of fellow. And then, of course, for us, for me, also there's my close sort of like a really dear colleague, Tom Banks. Many of you probably know. Certainly, faculty member will know that Tom Banks is really was a national treasure, but he died of GBM at the end of December 31st of 2019, and only a few months after he was diagnosed for GBM. So it's very deadly. No one can survive actually if it's in the later stage. And then John McCain also made the big difference in the presidential election, certainly in Arizona, because Cindy McCain, John McCain survived, basically endorsed Joe Biden, and then many other followed. So Arizona went to blue. So it has a lot of, so this disease has a lot of consequences in terms of the humans sort of suffering, and also in terms of political sort of like outcome, unfortunately, I mean, or fortunately, depending on which way you look at. So the reason GBM, the brain tumor, it's really a sort of like, it can be any place in the brain. Once it develops, in the early stage, you will not know. Once you already sort of have the symptom, it's always in the later stage. And then by that time, you just really hope the treatment can slow down the inevitable, sort of like a fatality. And that's sort of like without treatment, people may die in 5, 6, 10 months. Some lucky may survive longer. Even with treatment, the average is about 50 months. The reason is very simple, because the tumor, the cancer cells in the brain, they can move in the sort of, because brain, it's just not as sort of like, I mean, the brain tumor, like GBM, is like a semi sort of like a solid, also like sort of at the same time quite mobile. It can move around. And so anyway, I'm going to sort of get to the really core sort of like finding that through the experience we had in the last 12 years. We actually, our first paper I will show you in the next few slides, we really started sort of like this effort about 13 years ago, 12 years ago, when we have a colleague that continued to work with us. He's a chair for the surgeon and also chair researcher in the Barrow Neurologic Institute. And I will point out to his name soon. So because this is maybe an introductory talk to many of you, so I will try to keep the model simple. Many times also or researchers or speakers don't want to show the model because the models can be too complicated. Indeed, our first modeling paper has more than few equations, actually, altogether probably about 10 equations, because we're looking at every aspect of the movement or the interaction with the immune cells in the brain. But here I'm trying to keep it simple because we decide to return to the really basics. So we want to look at the simplest data we have. In this case, is mice data. And not even mice data, actually. It's Petri data. We had a paper on mice data about 3-4 years ago in a scientific report. I'm not going to talk about that because that more or less mathematically less interesting than what I'm going to present it now, and also but at the same time computationally more involved. So the one-dimensional equation is just simply it's because we're going to have a Petri dish growth, so you can really reduce the two-dimensional disk shape into the radial growth, and then ideally you want to have 2 equations, but then we find a way that you can use one equation to show the growth of the cells. Maybe I should go back and forth so you can. So this is the Petri dish. Well, I really should probably move this ahead. I shall use this. So this is sort of like the data we're going to use. So I'm going to get back to the second the slide. I'm sorry to confuse you. Really, at the heart of the, I guess, interaction of a clinical researcher and modelers like us is really trying to find the nice biomarker and understand the mechanism behind that, so we can really model the mechanisms, and then hopefully the biomarker quantity, the measured sort of like the value of those quantity or the measurement that can be used to validate the model, and then in turn we can use the model to make predictions, and that's really the foundation of sort of a really bona fide important modern exercise, but that's actually it's not easy to do. And we can use, again, the brain tumor, this GBM tumor exercise we had in the last 12 years. We actually start with data, but then the data turns out to be not allowed because my collaborator moved from University of Montreal, and excited called me. I don't know this person before, but then he read a paper we wrote published in Bioscience on the sort of like the tumor sort of like modeling on lung cancers, but then we talk about other things. And then in the United States, the data need to be approved before being used. And then basically they cannot approve data from a different lab. And also it's really US has a very, very stringent requirement in terms of really absolutely have no trace of patients. And then the data collection, who collect the data need to also to be on board. It's just a mess. We end up cannot use the data. So here we use some data that already reported. Well, the data was available in 2007, but then published in 2009, and we received the data in about 2009. Yeah, that's the time after 2008, because the also of the first also he's the PhD advisor was our former student, actually Professor Tracy Jackson in Michigan. Anyway, so the reaction diffusion model is commonly used, and then also it's a natural first candidate because the cancer cells do grow and also move around. And then in our case, the data is indeed has this symmetric sort of a profile of this, so we can use radial growth. And so we have sort of like the sort of best scenario of like trying to formulate a very simple model. And the biomarker, that's something we need to worry about. For many cancers, the biomarkers, like a prostate cancer that we worked so hard for so many years, it has the natural biomarker of the antigen specific sort of the specific antigen, the prostate PSA. But that's not the case for the tumor. Indeed, for the brain tumor, indeed, what we really want to know, if there's any biomarker that for the model, is really to find the diffusion rate, the growth rate, and the death rate. If you don't know growth rate, you are not in the business of modeling anything, because we are talking about the growth. And then because the tumor do move around, so we need to know the motility rate. And if you want to know the growth profile, for a longer period, then also you need to know the death rate. So minimum, we need to know these three rates. And so we actually not going to get that, because all we get is going to be just image. So we need to really find a way how to get these parameter values. And then so we actually did that. I was hoping to talk about this one, but then the model will be more complicated. So instead of talking about this one, so I'm going to just briefly describe this kind of interesting work, and then return to the simple modeling sort of exercise or project on the petri dish growth. So we call these parameter values the diffusion rate, the growth rate, the death rate as digital marks. But then our colleagues will say, well, you can just call this biomarker, because these are the ways that ideally, they want to take the bypass and then to perform experiment to compute that. But now if we can do it estimate by just looking at the image so much better. It's still biomark, although I still prefer for digital mark. So although I will be returning to the simplest model on the brain tumor growth on a petri dish, but I do want to sort of highlight because really the history was we start with complicated one, and then we start with some simple one on the petri dish, and then more complicated on the mice data, and then I'll get to the human data. So this is what I'm going to talk about, our latest work, but only in a few minutes, and then later on we will go back to the simplest model on the petri dish one, because then you know how much care we must exercise in order to really present or to come up with good model. And then once we do that, we can learn so much, and then other people may also interested in learning that. If you have something very complicated, you will get tired of before you even submit your paper, and then no one even probably want to read that actually. And so the sort of what you're going to see for patients, sort of like you are not going to open the sort of skull, I mean the brain to see the tumor. Usually you just have the MRI or other kind of scan, and then a good quality of brain sort of like image will show basically this kind of and this is one of the example. Like this is a very later stage. This is really marginal, whether or not, I mean, in this case, if the patient is old, probably it's best not to operate at all. And then oftentimes the patients are old. So we have a tumor. You can see these are brain sort of like parts, and then these are hair brain cells. And then here inside is what we call necrotic core, consisting of dead cells. The white sort of ring is more or less consisting of the cells that are actually reproducing, taking in the nutrients through the blood supply, and then producing more cancer cells. And then beyond that, there may be some cells sort of like shedding sort of out off from the boundary, from the edge, or from the what you see here, but also mostly the dark zone is consisting of like the high blood pressure, not blood pressure, high pressure raised the surrounding tissues, fluid, so we call edema. And then there's a lot of question of how to model this. It's actually very difficult, because then we need to introduce a way to measure the pressure. And it's just very difficult to do that. And it's everywhere it's highly pressured anyway. So what we are going to do is there's a lot of alternative ways for you to do what we call segmentation, to really classify the tumor in terms of dead cells and the living cells. And then you put those things together, and then into a spherical shape. Then you can estimate the radius of the necrotic core, and then also the width of the bandwidth of the shell that consisting of proliferating cells. And so we can make the correspondence of a traveling wave, because most time complicated or simple models, more or less, they're going to quickly develop into traveling wave. In this case, we have a traveling pulse. Then you can say that when the cells are of this density, we normalize into 1, then we can call this really the lighting zone, I mean the white zone. And so the bandwidth can be approximated by a lens. And then of course the edema has a lens, and then the core has another lens. So basically through image, you can come up with a 3 measurement: the core radius and the bandwidth of or the radius of the tumor. And so you can see the difference of, I mean, you can find the bandwidth of the ring, which is the radius of the tumor minus the radius of the core, the necrotic core. And also you can know the sort of like tail length that depicting the region, what we call edema. So with that kind of measurement, and then so the best hope is to find a minimum model that can sort of profile the shape of the scrolls in terms of traveling wave, and then using the traveling wave measurement of the peak width, I mean the 20% peak width, and then the tail length, and then and also of course this length, the magnetic core length with what we measured in the picture, and then that would be great. I mean, if we can have a ballpark estimate, and this requires us to have a model absolutely involve just a minimum or no any other parameter, or ideally just these parameters, and that's what we did. And this is a paper that I don't actually want to go into detail. So in order to accomplish that, you need to use what we call cross diffusion. So you have the diffusion rate, and then here you basically just use an almost like step functions to really model the birth and the death process. And so it's a paper already published, and we already find actually pattern for this sort of like idea, sort of like using traveling wave to extract these three parameters: the diffusion, death, and the birth rate for the cancer cells in a single image. Always, if you have two images, then even better. Then you can have a better quality in terms of estimation. So I just want to say that that's really the implication, the consequence of what I'm going to present in the next 20, 30 minutes. So this is only 20 minutes, but just showing that we are not going to sort of like saying that our mathematical work actually are not so connected to the clinical work. In order to have that connection, we want to start from something more sort of like more plausible or feasible for modeling effort. So that's sort of like we had a lot of papers. This is just we probably have about 10 papers on a brain tumor, but the talk today is sort of like immediately more or less focused on this our earliest work 6 years ago. Tracy Stebin, Professor Stebin is now in University of Florida. She's a tenure track professor there. And then my former PhD student, Erica Rado, she's now tenure track professor in UC Massachusetts. And then these are other professors all over the country. These are from Asian, and then this from actually Kazakhstan. And then more mathematical treatment of our extended or generalized model appeared about 3 years ago in Sign. And so you really can continue to sort of like find open questions, find in terms of mathematical questions and modeling effort. And of course, also challenging is to find good quality data. And then our really, as I mentioned, 12 years ago, we started this journey of trying to find a framework, modeling framework for not just modeling brain tumor, but mainly because of brain tumor, but also for many other kind of tumor growth. And then so the professor, Mark Brewer, is the one that from Canada, from Montreal University, excited to want to share with us the data, but turns out that he can't legally, because in the United States, he just cannot do it. And then this gentleman was a resident surgeon at that time. Now he's a chief surgeon in University of Alberta in Canada, the brain surgeon. And my former PhD student, he actually had training in cancer in Tufts University. He got his master's degree in cancer biology. But then his bachelor degree was with us, and the PhD degree was with me. And then he's now sort of like was chief scientist for BMS, Bristol Myers Squibb, and also many other sort of startup company. And then of course his friends, our former student, 5 years ago started this now very, very fast growing company called Applied Math. And many of you who really want to find a job or have an option outside of academia, you can contact them, Applied Math. in Boston area. And so this is our actually the first paper with the data. So what we end up strike the compromise is Dr. Pru are not going to be able to share with us the 86 patients data from Canada. So instead, so he spent the first 6 months collect a few patients data and shared it with us in Arizona, in Barrow Neurological Institute. And so we had this paper really cool in terms of model validation, but we cannot do really model prediction because we don't know how to, at that time, how to estimate the parameter using one-to image. We just sort of like, this patient sort of like had 3 surgery. You can see the first one much smaller than the one I showed you before, so was able to do it. And then after the surgery, of course, you can estimate from the search. I mean, basically, we use the patient's image here and then made estimation of what's the tumor cell density. The blue is low, and then the one cut off the red is very high. And then with surgery, what will happen? That's our sort of model simulation. And then that's what really happened. And this is model simulation. They're quite close. And then you can see the once after the 3rd surgery, this is already crazy. It should not be done. Then the patient is left to die. So we have to deal with the real geometry. So it's really completely computational. The model is complicated. We cannot do mathematical analysis. So we cannot gain much insight either because the complexity of the model and also the computational task. So in order to gain insight, we want to really have a minimum model. And that's really what happened. If you look at the mathematical models, sort of the contributions in medicine, like in diabetes research, the insulin glucose, they use a minimum model. Or even the MRI image, sort of like conversion, they also use a minimum model. Because when you have too many parameters, then you will have a noise, and these parameters can bring a lot of trouble for when it comes down to the prediction. And then we even wrote a very comprehensive modeling review paper, and it's very well received. And so now almost, I mean, more than 30 minutes down, I really want to, so that the information I really want to convey to you, but the next 20 minutes, I just show you that how that can be done through some very, very simple experiment motivated by the experiment. And then you basically try to really base your model formulation on that sort of data set. First, you want to make sure your model can describe the data, and then see whether or not the model can generate insight. And then none of them will be easy. That's why most time you don't see either in most of people's work. They just stay theoretical. They have data, they don't know how to use it because they know the model will not be able to describe the data. And then we know how tough it can be unless you have a very, very, I mean, I had the fortune to work with a very, very talented, hardworking student over the years. So this is sort of like experiment of sort of a growth of brain tumor just on the petri dish. That was there. Now many of us so like that kind of a petri dish. And then of course now they can do all at once with like 90 some sort of like replicas. So this is for E. coli growth. And indeed, what we learned from the brain tumor model exercise also find great sort of applications in modeling the growth of E. coli patch. Because E. coli patch, when it grow in the algae based or in the medium, it's just like a cancer cell growth. So 2 type of cells growing. One is the wild type, the native one. One is the sort of like the mutated one. So the mutated one in petri dish, they're actually more tightly sort of like a stay, less diffusive. The native one actually more sort of widely sort of like diffusive, but inside the brain it's the opposite will be true. So this is really so we cannot, so that's why, I mean, there's a word of caution. What you see in petri dish can be very different or opposite, and then what you see in mice can be totally disconnected from what you are going to see in human. But still, at least the exercise is here really not so much for brain tumor, more like for the cell growth, how to model cell growth. Most of people, mathematicians in particular, they just naively think that cells will follow what we call reaction diffusion equation of the wave equation. The diffusion is really driven by random motion. It's not. The driving is actually by what we call density dependent diffusion. Imagine that if you in a well, before COVID-19, we see every day when you're getting close to the campus, the traffic becomes so slow. When you at the 5 p.m. want to leave the campus, it's also takes so much longer. So when you have a higher density, the diffusion rate is actually the opposite. Will be almost ground into zero to slow. So what the reality oftentimes is complete opposite from what many mathematicians sort of like thought about, because many of us, like this person in particular, Andy Stan, he was trained as physicist, so he thinks the human cells or the biomass, we have like particles. They're not. Particles has a lot of space in between. There's no really cloudiness, so it's only the pressure. But for cells, they actually need to stay together in order to not being sort of like killed by immune cells or too close to the nutrient availability because they need nutrient. So space oftentimes is the premium. I mean, it's clouded. So very different thing. So I just trying to say that when you're trying to really model, you have to examine every single assumption, and then you realize the community, the modeling community, are quite disconnected with reality. If you take them from the textbook, those are not for your research. Those are just for really developing your more or less understanding of the mathematical tools or the basic modeling tools, not really for application. So this, I can spend a lot of time on this anyway. So what really at the heart of what I showed you our work about 12 years ago, the first framework for modeling the tumor growth is what we call go or grow. Oftentimes, when the cells has enough space and nutrient, they stay there, they just grow. When there's a lack of a nutrient or space, then they move. So it's not because of the moving through the gradient. So it's the physics is just not the same as biology. But then many people who sort of like modeling biological process, they are actually jobless physicists. I mean, they cannot find a job because the training really doesn't prepare them for that. But then they are very, very, I guess, ambitious or very naive when it comes to the modeling. And that's the case of here. Andy Stein is very smart, very hardworking person, but he didn't have the training of mathematical modeling. So he just put together a model as he see wish. And then, so he assumed the diffusion, the movement, primarily because of the random motion. Wrong. That's not true. And then gross logistic, that's fine. Although probably there's better choices like a compass model or one Bartolomé model or many other ones. But then that's fair to begin with. Taxing, yes, maybe, but whether or not significant, we don't know. Actually, it turns out to be very tiny. And this is really, he wanted to model, he can't. So he just invented what we call delta function, and assuming that the median, the radius of the core already known. And that's very silly because a good modeler don't need that. Your model can produce that. And then that value can be actually as expression of the other parameter, but he doesn't know that. Not him, not anyone know that. We don't know that yet. Until we very much towards the end of the modeling exercise, we realize what we can do better. And so he introduced lots of parameters. And then he has lots of data point. He has some not just day 1, day 3, day 7. He probably have a few more, but here we just show that at least 4 data points or 3 data points. But then, of course, we a bit tough. That's why he just cheated here. I mean, put the value in instead of using the data to do that. And what we do, we want to just use the data point and not sort of like assume that you already have the RT. So basically, we have a lot of questions that we think we can do better, or we should try to do better. The biological questions, of course, do we really need those separate equations for such kind of simple sort of like a cell growth scenario? Otherwise, then you imagine in a real life situation will be much more complicated, and your model will be out of control if you cannot understand the model via through math to science. Because my understanding of a scientific sort of like endeavor is trying to find the simple rules, find the simple sort of like patterns that among complicated sort of observations. You don't want to add complicated system to what already complicated observation. So we basically think we can do better, or hope we can do better. And then of course we also, as a mathematician, we want to prove theorems in order to gain insight. So we have a lot of questions on that, but I don't have time for that. So I'm going to just focus on that. This is something I want you to, if there's any sort of like single, sort of like a take-home messaging from the modeling exercise, not from what I speak 30 minutes ago. For this simple modeling exercise is that density-dependent diffusion is what you really should take when modeling biomass growth or cell movement, not constant diffusion. In fact, the D1, D2 almost is the same. So when the density high enough, A is far less than you start. So this almost became 0. The diffusion, the reality is the diffusion, when you can see the diffusion function is very, very high and then quickly became very low, almost to 0, when the density approaching, like here, the half of the density that possible for the cell. And so that's something very important. But then the problem is it introduced a lot of mathematical challenges, including existence of uniqueness theorem. No one have even done that because mathematicians always assume constant coefficient. And so all the machinery they learn from textbook can be used. And then, but for doing research, you need to know more than textbook. You need to be able to really be creative to expand on that. So we sort of 2 or 3 years later on, we wrote a paper on existence uniqueness of solution of density dependent diffusion. But that's highly technical. And most of you probably don't want to get that because you need to spend probably years in starting differentiation function analysis before you can even understand the machinery of the proof. But anyway, so we want to introducing the core concept is the density dependent diffusion. And then here we still put in just to see whether or not this is small or big. We want to use logistic equation because it's simple for mathematical analysis. Later on, we did remove that. The paper we published last year was able to assume very, very generic growth equation, not the simple logistic equation. So that's sort of like the simple modeling framework. You want to, so let me put this way. Okay? So many times people have equations very complicated. The reason they do that is because they only want to do computational work because they know nothing, even the simplest model. So they pretend that they're smart. I mean, they're sort of cool. They can have the complicated equation, but very difficult to study mathematically. If you cannot study mathematically, it's very difficult to generate insight. If you don't have insight, you don't have understanding. You just have a snapshot. And that's actually even fake one because they're not a real one. So that's why, I mean, in the society now we know there's a lies, there's stemni, there's a statistics, and now the worst lie is modelers. And we see what happened last year in April into the COVID-19. Basically, all the modelers they provide, they produce all kinds of silly predictions, end up really ruining the scientific community for good for many years to come. I mean, our state governor in April already said that we are not going to listen to modelers because we have a bunch of modelers. Really, they are no good modelers. They know nothing, but then they still dare enough to make predictions, and many people did that. the New York governor just the last month really very vocal. I mean, of course, a year ago, he was very vocal saying that the model is all wrong, completely wrong. It's because it's not easy. So, of course, we have to give the benefit to the modelers that because they scare the society. So, in that sense, that maybe help the society, because otherwise things will be worse. I doubt though, because I doubt how things can be much worse than what we experienced in the United States. Just that side remark. So modeling exercise is non-trivial. You can start sort of like something very, very simple, but you really need to work hard to try to iterate the model. And we iterate this a few times. First, we also have a linear diffusion and with other kind of nonlinear growth, but it turns out to be not. So the whole exercise took actually modeling alone took 3 months. And so what we want to do is really want to establish the profile of solution, but not that going to provide the a good match with what we see in the image of the petri dish, the petri dish growth of the brain tumor. So we use the data measured the initial. You can see the initial sort of like size is about 20 microgram micrometer, and then grow. Basically, we can have the data point, the value for the later on for model fitting. And set up easy. You can. So I have 2 collaborators here. Tracy, now the professor in the University of Florida, and then Erica, professor in UC Merced. So Tracy wrote a PDEP model, and then Erica, she actually wrote a difference equation model, and both matched very well. You can use PDEP model because routine, that's really very easy to write the code, and actually it's very, very good, very robust. You just need to be careful when you describe the step size. Make sure the step size is very small to begin with, or at least always try the small, very small size until you see the solution profile doesn't change much. So there's a lot of things you can learn, you can enjoy, you can have fun. And so with this one, I'm not going to introduce the math if you don't know this before, but if you do, the reason traveling wave solution is such an interesting topic in mathematical community is because you can quickly sort of turn the PDE equation into a system of ODE with boundary condition. And that's non-trivial, but that was very well studied 50 years ago. In fact, the most mathematicians that they interested in math biology because of that, because of traveling wave phenomenon. And because the training in the 50s, 60s was actually about the boundary vary problem. So they put that into good use. And then I can spend a lot of time on that too. But what I could, so the travel wave solution really take the form of like, you start with high density and then the things move. Maybe I can try to see if I can use the tool of drawing, answer tool. So basically, if you start with a density profile like this, and then given time, the cells grow and move, it became like this. More time, it's like this. And so that's what we call traveling wave front. And of course, also go this side. I'm not going to talk about this. So that allows you to use this as a wave variable, and then to convert the PDE into what we call waves equation, second order equation. If it's a single equation, if it's system equation, then you have many second order equation, and then will be very complicated. And then in order to study the second order equation, we like to convert into a system of first order nonlinear equation. And you just introducing the new variable, a W plan. The W is the wave variable. So we now call this way. So U, of course, is the density of the tumor, and then density grow. No, according to this, and then the movement, because density dependent movement. So this is together is density dependent, and this is a convection. Okay. And then traditionally, you want to look at whether or not mathematically it's feasible to have traveling wave solution. Traveling wave solution typically is what we call heteroclinic orbiter connecting one center point to a stable node. So usually, so you want to show, you want to see whether or not the equilibria, we have that kind of a nature. And here we have two equilibria, and then the traveling wave will probably have to be connecting these two. And then the hope is one will be saddle and the one will be stable node. And then in order to have that kind of nature, the stability of those two steady state, I'm going very fast because I'm also running out of time. So we will just need to examine the Jacobian. And then if you look at this one, the trace of course is negative if you see is bigger than mu. We is the, actually I mean the nu. Nu is very small, so C will be faster than that. Okay, so this will be negative. And then, but then you look at the determinant is less than 0. So yes, we are happy to have a 1, 0 is a center point because we need 1. And once this center point, there's nothing you can do. It's a center point. So you are hoping the 0, 0 will be a stable node. And then, to be stable node, you realize that you are going to have the eigenvalues. Node is not stable spiral. Because stable spiral, you will have at the 0, 0. If it's stable spiral, then you have a solution become negative because U is the density cannot be 0. So you want to have a solution sort of like go this way. Actually, in our case, the phase plan will be a U, this V, and then this is a 1, 0. So I really, because this is you can pick up in a EDE course, and so the heteroclinic orbiter we are connected. I cannot move that. Once after a few seconds, it starts to sort of like freeze out the whole thing. So heteroclinic orbit is basically connect this 1, 0 to 0, 0 in the bottom, because if you put a minus y, then your phase plan of analysis will be on the positive column. So these are just mathematical sort of like details, and then you will realize that the discriminant must be used if you're using the quadratic formula. You want to have this sort of like positive in order to have two negative eigenvalues, and that sort of give us this condition. So the minimum wave speed will be this value, and then in terms of original parameter, then you take this form, and then sort of this is just a routine computation. Once you understand the topic, then you can go through that. But then in order to prove rigorously there's a heteroclinic orbiter that connecting this, then you need to use what we call sort of a trapping region to show that the solution state in this trapping region, in this case, is a triangle. And then you need to show that the solution indeed goes into that and stay there. And then the unstable manifold, once leaving the steady state, it's staying there, and then it keep going sort of like leftwards because the V plan or W plan is always less than 0 because it's below. So mathematically, you can show that it's a trapping region, and then you can prove solution always goes in, but it's non-trivial. You need to, of course, select some alpha, not alpha. This slope has to be very carefully chosen. It takes a lot of computation. We actually end up was unable to do that for 2 weeks until we use Mathematica, and then later on we use sort of like a manual computation to demonstrate that this is indeed invariant region. And then, of course, in order to find the parameter value, now people will call this machine learning. This is really optimization algorithm that very, very well known in statistics, and then utilized them in the MATLAB community. And so this F-bin search, it's become a routine. And then you basically minimize our LO function. LO function, you can decide what LO function, how you going to weight the sort of like errors among all these points. And so we use more or less sort of like the relative ratio. And for that, we're able to also show that all the parameter value that we have so far are all sensitive. So we have to keep them all. And then the fitting very well. So these are the data points. So as you can see, he has a lot of data points. That's about a dozen or more. And then so the experimental data, not a dozen, yeah, about 10, about a dozen, yeah. And then Stein, his model, that very, very problematic model, able to fit the data very well. But then our model is less parameter, but also much more sort of a biologically meaningful, and the mechanistic formulated model does just as well, if not better, actually slightly better by looking at the error. So we're happy on that. And so you can see the traveling wave solution, and you can talk about the speed. So that just shows that this modeling exercise demonstrates that you have to use density-dependent diffusion. And then so that's what sort of like matters if you really want to using patient data too for that. And then, of course, what we had talked about before is that if you don't have enough data points, just one image, then you have to have something what we call minimum model. And this is not minimum model. This is just one-dimensional model, and with one equation. But then we have 6 parameters. And then, but then we are happy that we were able to balance our needs. We can fit the data, understand the model, prove theorems, and gain some insight. And then also can generate a sort of hypothesis. And later on, of course, we really examine how the density-dependent diffusion matters most when you're trying to match the wave speed at the forefront. And then I probably, yeah, can more or less end here. So the model, we banded generalized model in the most recent paper. This is just published in a few months ago. The analysis is more rigorous, and also we present more detail. So so that really, if you really are mathematical, sort of like researcher want to do mathematics to prove theorems, then this paper is actually more readable, and then you can learn a lot more. And I really don't have time for the 2 population model because I spent so much time to motivate or to talk about our more sort of clinically related to the work. But just want to say that if you want to write a PhD thesis on such kind of topic, then you can really go to the full sort of length of studying 2-dimensional 2 population model, and then but the mathematics became a lot more interesting, also a lot more involved. We spent a whole year on that, and then of course resulting in the publication of the paper in Science. I'm sorry, and also there's a lot of interesting topic about minimum speed and maximum speed that hopefully that close to the real speed. And that's also a concept that no one talked about before, but through our work, we are able to introduce this concept, the maximum speed, so we can have a envelope estimate the lower sort of estimate and up estimate for the speed. And so, yeah, that's and then you can do a lot of phase plan analysis if you are interested in proving theorems. There's a lot of such kind of a challenging work that can merit for PhD thesis in mathematics. So I just want to end here for the acknowledgement of the support we received, and then if you want to know the 2 references, I mean, this is I spend most time on this, and the experiment is on this. It's from this paper, and we didn't really have time to go into the lens of the more mathematical details, but I think that really should be left for you guys to decide to read or not. Thank you for the attention. I used all my 1 hour time. Thank you.
All right, wonderful talk. Let's thank the speaker. Thank you so much.
Thank you.
Okay, at this time, I'm asking anyone that has any question, if you want to ask, please feel free to ask now.
So I should keep the paper here. So you can always do the print, the screenshot, but also feel free to contact me if you have questions after the seminar.
Minä go ahead.
No, please, you want after you.
I could wait, Jay. I mean,
I insist.
Thank you, Jay. Thank you, Yang, for this nice introduction of your work along the line on the mathematical modeling of this brain tumor. I mean, I may have a couple of silly questions because I really don't know much about the research in this area. First question is really just, I see at some point you use the time unit as day, using day as the time unit, right?
Right, time, the day, yeah.
And just want to have some idea. For your patient, usually what would be the time window you would monitor the progress of the development here?
In terms of week. In terms of week, and then they usually go back, check every month, and then
okay.
Yeah, they can subject to a more frequent MRI image, but then they usually because it's really the insurance don't want it, it's so expensive to treat, so they check on monthly, like the prostate cancer will be actually every 3 months. They even mention the time. So all the patients, when they feel sort of like so much pain, they go back there.
Yes, and so far the model is about monitoring the progress of the tumor. Have you used this model kind of like embedding some treatment here?
Yes, we did for the, not so much for the GBM, even our earliest work, we talked about potential treatment, but we don't have the data. So this is paper, yeah. So you can see, so we did talk about the treatment, but then hypothetic treatment, yeah.
So of course it's the even the first step in the monitoring the progress of the condition is already a breakthrough. And then I just was curious about here.
Yes,
about
yes.
this.
We start on an ambitious path, because at that time Stefan was an undergraduate student. Undergraduate student has no fear of, and he just wanted to do the real thing. But then of course, yes, you can do the real thing, but you don't get much understanding. So we go back to the simple thing to see what we really understand and what we don't.
And another perhaps silly question is, there are many types of tumors, right? So I kind of just curious if there are some special features of the specific type of the tumor. You call it GBM, right?
Yeah.
And do you think the method ideas you used here can be shifted to model different types of
that's exactly. Yeah, this is that's why we have this. This is a generic framework. We started want to apply this for GBM, but then we didn't have data, so we wrote this generic sort of like framework. So the what we call go or grow. So either if you cannot grow fast, then move, then go. So yeah, sure. So what we use, this one is a stem from this general one. So all you can say, because we motivated by the brain tumor modeling sort of like exercise, so we produced this framework, and this is being applied to many other things, even to ecological applications, like the invasion of a foreign species, or the sort of like epidemiology model. So how the disease spread. So it also can take this kind of form. You either you decide not get treatment, or you find a treatment and then in the process you spread to other people. Okay?
Thank you.
Thank you.
Yeah.
So I really apologize if I missed this. Maybe you said something about this at some point. But did you look at all at the stability of the traveling waves, or is there a good stability in this setting?
We did look, but then we didn't publish that. We look at that. In fact, my student, she only put the very first sort of like few trial, not great success because we have to include in a lot of conditions, the compact support for the initial condition in order to, and then with additional technical conditions. We didn't publish anything on that.
And was that like an Evans function kind of approach, or something else?
No, we used basically the boundary sort of like a very problem approach. You used you basically compute the largest eigenvalue of the stable unstable mode. I mean, you're trying to show that the large
Approximating by a compact domain or something?
exactly.
Yep. Okay. But so there's still a lot of work to be done there in terms of stability.
Yeah. We didn't like our work, so we didn't even bother to write for publication. So it's just buried in her thesis. Yeah.
Okay, thank you.
Okay, any other questions? Anybody else has any other questions? Okay, well, let's thank the speaker one last time.
Thank you. It was really a pleasure. Really enjoyed the interaction with you guys. Thank you so much.
No, thank you for coming to visit us today and sharing your work. It's really great for us down here at FAU to have such wonderful visitors.
Thank you again.
Thank you.
Thank you, Yang, for